Hello everyone and welcome to my talk on nanotechnology and nanoparticles. I am Amal Madhav. I'll be your guide today. We'll begin by defining nanotechnology and why working at nanoscale is special. Then we'll explore the history of nanotechnology and take a look at different types of nanomaterials, their unique properties, and finally we'll cover the real-world application, discuss the advantages, challenges of nanotechnology, and consider the future direction we can take in this field. So by the end, you will have a clear understanding of why nanotechnology is such an important and exciting field. So let's begin with the basics. What is nanotechnology? So here is the definition. Nanotechnology is the manipulation of matter at least one dimension sized from 1 to 100 nanometers. At this scale is commonly specifically known as nanoscale. For reference, nano comes from the Greek word for dwarf, highlighting how tiny this scale is. A nanometer is 1 billionth of a meter, that is about 100,000 times thinner than a human hair. And at this scale, even small changes can cause big differences in how a material behaves. Essentially, nanotechnology is the science of building and studying materials by atom or molecule by molecule. So let's check why nanotechnology is special. And you might wonder why this nanoscale matters. Well, when we shrink a material down by a few nanometers, new effects appears. Quantum mechanics, the physics of very small particles begin to dominate as materials, and a material surface to volume ratio it increases very enormously. For example, a human hair is about 100,000 nanometers wide, but at nanoscale, those quantum effect and immense surface area dramatically change behavior. This can make a material stronger, lighter, more chemically reactive than in its bulk form. So, in short, materials at nanoscale behave in completely different and useful ways. This is why this nanoscale is so much exciting. So, we'll have quantum effect dominates and surface to volume ratio increases drastically and electron motion changes, and also the optical and electronic properties become size dependent. And let's check the history of nanotechnology. Okay, let's look at the history. In 1959, during his Nobel acceptance speech, Richard Feynman gave a talk called There is Plenty of Room at the Bottom, where he suggested we could manipulate individual atoms, a visionary idea at that time. So let's say this term nanotechnology was first used in 1974 and by Norio Taniguchi, but it was not widely known. Still inspired by Feynman's concept, Dr. K. Eric Drexler used the term nanotechnology in his book Engines of Creation, the coming era of nanotechnology, and which achieved popular success. The book achieved popular success and helped nanotechnology into the general public. And in the 80s, the invention of scanning tunnel microscope allowed scientists to actually see and even move single atoms. And for example, like using its tiny tip to push the atoms around. These breakthroughs kicked off intense research in nanotechnology, and by the early 2000s, the field has become a global research boom. So let's look at the major branches that nanotechnology has achieved. So nanotechnology is a broad field and can be organized into different branches because of its impact or industrial application. So for instance, we'll have nanoengineering, which involves creating and manipulating structures at atomic scale using tools like advanced microscope and precise fabrication techniques. While green nanotechnology is about sustainable applications such as improving the efficiency of solar cells or water treatment using nanoparticles. Well, we have wet nanotechnology, which applies nanotech in biological and medical field. For example, creating nanoparticles for targeted drug delivery, advanced diagnosis, and each branch combined physics, chemistry, and engineering to solve problems at the nanoscale. And since we know about the major branches now, let's look at the types of nanomaterials. And nanomaterials can come in different types based on their composition. So we'll have two types of classification, and first based on their composition, then we'll look into the types based on their dimensions. So first we'll have carbon based nanomaterials. And their examples are given: graphene, carbon nanotubes, fullerenes, carbon nanofibers or CA, and carbon quantum dots and nanodiamonds. And also metallic nanomaterials that includes gold, silver, copper, iron, platinum, palladium, nickel and zinc nanoparticles. And ceramic based nanomaterials, that's titanium dioxide, silicon dioxide, alumina Al2O3, xenon, cerium oxide, SiC, and boron nitride, etc. And next we'll have polymeric nanomaterials, and there include polymer nanoparticles, dendrimers, nanofibers, nanogels, polyaniline, polypyrrole, and chitosan nanoparticles. And afterwards we'll have there are also biomolecular nanomaterials which made from proteins or DNA structures. Each of these categories have their own unique properties as well as their own uses. And another way of classification I have mentioned right like 5 minutes ago is based on the dimensions. So we'll have zero dimension, and in this case, zero dimension, all the three dimensions of the particle are in nanoscale. The examples are nanoparticles and quantum dots. When you talk about quantum dots, just imagine tiny dots. This is an image in scanning tunneling microscope. And next is one dimension, and these nanomaterials are at least two dimensions in nanoscale and one dimension is comparatively larger. For examples are nanowires and carbon nanotubes. And next is we have discussed 0D 1D. So obviously next is 2D. So we'll have only one dimension is at nanoscale while other two are comparatively large. Examples are given like graphene, which is a single sheet of hexagonal carbon atoms, and the three-dimensional, and also we'll have other thin films. Next is three-dimensional, but in this case there is a difference because 3D nanomaterials have no dimensions strictly at nanoscale. They contain nanoscale structures or as composites. For example, nanocomposites with nanoporous grains. Or here I have given a picture of nanostructured bulk materials where we occlude nanomaterials into polymer molecules and to get nanocomposites. So let's look at the properties of this nanomaterial. So the first, nanomaterials often have unusual properties compared to the same material in bulk. A big reason why this is happening because the larger surface to volume ratio. You can see the images here as the volume volume to surface to volume ratio increases as the size decreases. So let's say nanoparticles have their enormous surface to volume ratio. That is, nanoparticles have far more atoms exposed on its surface, making it more reactive. For example, we'll use nano-sized platinum for catalytic activities. And with this case, we can also have atoms that are mechanically stronger. And also we use the same property can be used for biosensors also. Also next is the quantum size effect. As we mentioned about the surface to volume ratio, then if the particle size is becoming very small, I have mentioned the physics of smaller particles. The quantum mechanics dominates the behavior. So we'll have size dependent optical and electronic properties. So with respect to this, we can have quantum dots that change color depending on size. And we have a key relation here where the electron energy is proportional to 1 by their size square. And you can see the electron energy. First we have a condension band and a valence band in the bulk material. Later it transforms into individual energy levels as the size decreases. So overall, shrinking at nanoscale can give materials new and enhanced properties. We look at some of the other additional properties also. So that includes enhanced mechanical strength, unique electrical properties like improved conductivity and semiconductor nature, and distinct optical properties. As I know, color changes with particle size, and lower melting point, improved chemical reactivity, and special magnetic properties. We call it as super paramagnetism at nanoscale. Now let's look at applications of nanotechnology. Nanotechnology might seem like a modern field, but people have used nanomaterial for centuries without even knowing it. A famous example is a medieval stained glass. where artisans added tiny particles of gold or silver to create rich red and green colors. Another is the ancient Lycurgus cup in the 4th century Rome, which appears to be one color in reflected light and different color in transmitted light. You can see this picture over here. And another is the Romans and Greek, which use minuscule crystals such as sulfide nanocrystals change their hair color. These examples show that nanoscale effects were exploited long before we had science to explain them. So now we can see the science behind these beautiful effects. So let's look at the applications in our day-to-day life. And nanotechnology applications found in various fields, like for example, in medicine, it enables targeted drug delivery and better imaging. In electronics, nanomaterials makes computer chips smaller and faster. Nanotech also improves energy and environmental technologies by enhancing solar cells, enabling advanced filters for water and air purification. In agriculture, we'll have nanofertilizers and pesticides that boost crop yields. And in manufacturing, it leads to self-cleaning surfaces and lighter, stronger material. Even consumer products such as sports equipments or clothing can incorporate nanotechnology. For example, you'll have silver nanoparticles that prevent bacterial growth and odors, and also we'll have graphene particles which constitute to making armors and all. So these examples show how nanotechnology enhances many products we use daily. So let's look at the methods of producing nanoparticles. So basically these methods, there are two main approaches, we can just classify them. First is the top down and bottom up. In the top down approach, we'll take it from the top. That is, we'll take a bulk material and break it down into nanoscale pieces. For example, we'll have lithography and milling. Such a milling which is used for making computer chips. Now bottom up approaches, we are building from atoms or molecules, usually through chemical reactions or cell assembly, like growing nanoparticles in a solution of wafer phase. Each approach has its pros and cons. Top down can be very precise but may be wasteful, as a lot of material is going to waste, while bottom up can be efficient and create nanoparticles but are harder to control exactly. In practice, the scientists use the combination of both strategies to get the best result. And in this flowchart, it's given like most of the techniques that's used in this field. Now let's look at one of my subtopics I have here, nanoparticles. So what are nanoparticles? Nanoparticles are particles between 1 and 100 nanometers in size. They can be made from metals, carbon structures like nanotubes, polymers, semiconductors. Because of their tiny size, nanoparticles have unique properties. A material at nanoscale can behave very differently at bulk. We call nanoparticles as zero-dimensional nanomaterial, since their all dimensions are at nanoscale. We have a lot of examples like gold nanoparticles, AUNPs, and silver nanoparticles, AGNPs, etc. And also you can find some of the nanoparticles in nature also, like volcanic ash, or like in an engineered product. We'll use it for in other engineered products like sunscreen and electronics, etc. So let's look at the classification. We can have the classification in categories based on their composition. So we'll have carbon based one that includes fullerenes and carbon nanotube, and the metal based one which I have mentioned earlier, called gold and silver. And also we'll have ceramic nanoparticles which use metal oxides, titanium dioxide and zinc oxide, and the semiconductor nanoparticles which include quantum dots, for example cadmium selenide or silicon nanoparticles. Then we have polymeric nanoparticles, and which use polystyrene nanoparticle, and lipid base which is formed naturally, we extract from naturally. And for example, we can see here gold nanoparticles are often used in medical cells, and quantum dots are used in imaging and other display applications. Now let's look at these applications of nanoparticles. In medicine, nanoparticles engaged in targeted drug delivery and enhanced imaging. In electronics, they allow smaller and faster chips. And novel devices like quantum dots displays. And nanotechnology also boosts energy and environmental technology. We have water purification, air filtration, and pollutant removal, and even have oil spill cleanup in the oceans. and also energy sector I mentioned. Then industrial and material science to create stronger, lighter, scratch-resistant material and smart textile. Then we'll have agriculture and food. In short, nanoparticles bring significant advantages from across many fields, from healthcare to sustainability. Now let's look at the advantages, risks, and challenges. So, in nanotechnology offers many advantages. For example, we have mentioned targeted drug delivery, smaller and faster electronics, and more efficient energy technologies, etc. And also have environmental protection, stronger materials, and agriculture improvements. As much as these advantages, there are also potential risks and challenges that we need to overcome to get better at this field. So let's look at this advantage, this cons and challenges. So this potential risk will have we have health risk because nanoparticles are so small they can enter the body or the environment very easily, possibly causing unknown health or ecological problems. There are also ethical and safety concerns, like such as privacy issues with tiny sensors or lack of regulations, and practical challenges like high cost and difficulty of the scaling up of the production. And researchers are actively studying nanoparticle safety, and regulators are being proposed to standard to address this issue. In short, nanotechnology has greater potential but also must be developed carefully to manage these risks. Looking forward, the future of nanotechnology is full of possibilities. And we can see the nanorobots working in the medicine to target individual cells or smarter materials that helps to adapt with different environments. And we can even have advancements in quantum computing. For example, nano-engineered fabrics might change their properties response to temperature, or materials could self-heal when damaged. In conclusion, nanotechnology is a revolutionary field which is already transforming science, engineering, and medicine, which holds vast potential for future breakthroughs. However, it is crucial that we pursue this technology responsibly, addressing safety and ethical consideration. Thank you all. That concludes the discussion on nano introduction to nanotechnology and nanoparticles.